All right, we should get going again. The next speaker in the morning session is Shintaro Kuroki, who will talk about classification of locally standard torus actions.
Okay, thank you, Stephen. So first of all, I'd like to thank organizers, Taras Fanov and John Beckson, and Mr. Jeffrey for giving me this opportunity to speak here. So I'm very happy to come back to the Toronto. And actually, this work, this is joint work with Yael Kashon. This work it started from when I was in Toronto. So recently, this is close to the end. So I'm very happy to share this work in this time. So microphone doesn't work. Okay. Yeah. So how about this? Still doesn't work. You got it. How about this? Can you hear me? Okay. Okay, let's start my talk. This is joint work with the passion. So this is the title of my talk, classification of locally standard torus actions. So let me start from the definition of the locally standard torus action. So this is assumptions in this talk. We assume that this T is a D-dimensional torus. And we distinguish T and this bold T. This bold T means that the standard torus. So this means that just a unit circle, product of D, this product of the unit circle in a complex number. And M is on a smooth manifold. And this T, this D-dimensional torus, acts on smooth manifold smoothly and effectively. So this is our assumptions. And what is a locally standard torus action? So locally standard torus action is defined as follows. For any point of the M, is a manifold M. We say this point is an X. This X satisfies the following two properties. The first property is its isotropy subgroup is a subtorus. So it means that it's connected because T is an abelian group, so its connected subgroup is a torus. So this means that there is no finite group appears in the isotropy subgroup. So this is the first condition. And the second condition is its isotropy subgroup. So this H fixed on a point X. Then this action is lifted to the linear action on its tangent space, TXM. And this split into the non-trivial part, P alpha 1 to the P alpha K, and the trivial part, this is an alpha dimension M minus 2K. And this non-trivial part, we can represent it some one-dimensional representation, says alpha 1 to alpha K. There are bases of the character lattice of the dual of the real algebra of H. So if this H dimension is K, then we can take alpha 1 to alpha K at this basis. So these two are the conditions of the locally standard torus action. Of course, we can also take K equals 0. In this case, this isotropy subgroup is trivial. So this action, this orbit is a free orbit. So this is our definition of the locally torus action. So actually, this is not familiar definitions. So actually, this is equivalent to the familiar definition of the locally standard torus action. Why we call the locally standard? So we call this TD acts on the standard coordinate with Cn times TL and Rm. It's called a standard action. Actually, we assume that this D is equal to N plus L. And so TD, standard torus, acts on the Cn times TL part standardly. So first, more precisely, it's first N coordinate acts on Cn as a scalar multiplication. And the last coordinate TL by the usual multiplication, because this TL is standard torus. And the previous definition of the locally standard is equivalent to the following definition. So it means that for any point, there exists a locally standard features. So more precisely, for every X in M, there exists an invariant open subset UM. This is an open subset of M. And also invariant open subset is omega. This is an open subset of the standard chart. Okay, and this omega has a standard torus action, and this and omega are weakly equivalent diffeomorphic. Weakly means that it's an equivalent diffeomorphic up to isomorphism. So this isomorphism is given by rho alpha 1 to alpha d. So now this T may not be a standard torus, but there is an isomorphism to the standard torus. Then via this isomorphism, they are equivalent diffeomorphic. And this alpha 1 to alpha d is an, I'm sorry, point. This alpha 1 to alpha d is a basis of the character lattice of the dual of the Lie algebra. And we often write this one-dimensional representation of the T. This small t is an element of the this usual T. And this T sub is upper alpha 1. Means that it's a one-dimensional representation of the T by alpha 1. And this is line from T alpha 2 and T alpha 3, T alpha d, something like this. And so this is called the local standard. And actually, I would like to point out that this is equivalent to the definition of the P-mirror. I will also introduce the work of the P-mirror later. And the P-mirror is also a study of the classification of the local standard torus actions. And in his book, in his paper, this kind of local standard T action is introduced. So before his paper, usually local standard means that it's just this TD acts on this CD part standardly. But this definition is generalized from that definition. Okay, so this is a local standard action. And let me show you 3 examples. The first example, okay, this D is an always dimension of the T. And the first example is, of course, it's a toric manifold, because this is a toric topology conference. Toric is one of the typical examples. So in this case, for each point of M has an local standard chart, which is isomorphic to CD. So in this case, we can take it's an TL part, TM, RM part as a trivial space. And there is, of course, another kind of examples. This is a very basic case of the moment angle manifold. So it's an odd dimension sphere of the CD. And now CD has an TD action. This may not be a standard action, but there is an representation, isomorphism to the standard actions. Then this TD acts on this CD. Then this has one of the example. This is one of the examples of the local standard action. So in this case, there is an some circle subgroup in this TD which acts on freely on this odd dimension sphere. So in this case, there is a non-trivial TL part appears in the local standard chart, but still RM trivial part is doesn't appear. So in the third example is this one, principal TD bundle over X. So on TD torus acts on the fiber freely, and this base space is torus acts on this space trivial. So it means that in this case, as a local standard chart, CN part is trivial and TL is just this coordinate. And we can also have a trivial RM part in this example. And moreover, we can construct many examples by combining these 3 kinds of examples. Okay. Mm-hmm. No, no, okay. Because it is principal orbit has no fixed point. Yes, tangential representation. Right? It's an I mean, I consider the isotropy representation. Yeah, not the tangential representation of fixed point. So in this case, isotropy representation is always trivial. A standard means the previous acts on the standard in the first n coordinate, first d coordinate. So is it not satisfied? Mm-hmm. Yeah, that's right. Yes, example 1 has a fixed point. So our standard action is this one. Local standard, yeah. Yeah, there may not be a fixed point if this n plus L is 0. Does it make sense? Okay. So this is one. This is an isoperiod representation. This is not the tangential representation of the fixed point. This is for any point we can take. We must satisfy this kind of conditions. Okay, does it make sense? Okay. Anyway, it's.
It is something called the standard action.
The standard action. This one. Yeah.
There's no catch.
Yeah, in the usual definition, this toric manifold is called a standard action, but in our action, it's a more general cases with more general cases. Okay, can I continue? Okay. Okay, so this is today's goal. I want to classify this local standard T manifolds up to equivalent diffeomorphism. So this is an important part. We want to classify it up to equivalent diffeomorphism. So to state our main result, I will introduce three invariants. Probably this is all already well-known invariants. So the first invariant is a quotient space of the torus actions, quotient of the T manifold. We often denoted by Q. And actually, the important point is this Q has a smooth structure by the functional structures from the M. And this is also called a quotient differential structure in Yael's talk. And the important point is this is isomorphic to the manifold with corners. The manifold with corners has a smooth structure itself. So how can we get it? So now this M has a local standard T chart. So we take local standard atlas, and UM is one of the charts. This is weakly equivalent diffeomorphic to the omega. It's an open subset of the standard chart. And this UM goes to the UQ. UQ is an open set of the Q. And by this standard atlas, we see that this UQ is diffeomorphic to some open set of the Rn positive O times Rn. And this Rn positive O times Rn is coming from the standard T action. And the important part is as follows. So first, we see that this is more than a manifold with corners. This also has the structure of the manifold spaces. So it means that for any depth k point, now this scale, this is a notation of the manifold with corners. So let's take the point from the point P from the UQ. Then we have some chart written by Rn positive O and Rm. If there are 0 coordinates in the Rn positive O of this P, of this image of P, then we call it the depth scale point. And this depth scale point, the manifold with spaces says that this depth scale point is in the exactly k facets. And k facet is a facet means that now we can also think about the depth 1 point, which is just only one coordinate is 0. And the connected closure of the connected component is called a facet. And so depth scale point is in intersection of exactly k facet. So this gives a structure of the manifold faces. And we also remark that now this projection may be regarded as a smooth projection. So in that case, there is a standard TD action here. And this is smooth map. So we may regard this as a smooth function. So by using the classical Schwartz theorem, we see that this theta can be expressed by this explicit formula. So it means that the first C1 to Cn, this is a Cn coordinate, is equals to the norm squared. Because it's a smooth, we need to take a squared. And this B1 to BL is on the middle of this TL. Actually, this TD acts on middle TL freely. So this B1 to BL vanished. And in the first final, Y1 to Ym is a coordinate of the Rm. and TD doesn't act on Y1 to Ym. So this is an identity. So we can regard this projection by this way. So we call it a standard projection. Okay.
Right-hand vertical map.
Mm-hmm.
Just to clarify, what is theta inverse of 0?
The inverse of 0.
Column. What is theta inverse of 0?
The inverse of 0 is an 0 is in a positive Wilson or also RM.
Yeah.
It's an TL. The TL is a middle TL. Does it make sense?
The T1.
TL. I'm sorry, this is L. Yeah, it's a free part. Okay, okay, let's continue. So this is the first example, first invariant. And the next invariant is called the univocal leveling. And this is a function from the, we denote the depth 1 points of the manifold with corners by these notations. This notation is by these notations. And the univocal leveling is a function from this depth 1 point to the this one. It's an T hat is an primitive element up to sign. Okay. So actually, this is an called characteristic function in the Davis and Januszki's paper. If Q is an facet, but this is slightly different from their definitions because their definition is a function from the collection of the facet, but our definition is a function from the point of the facet. Okay. And how to define it? Okay. Difference is an Davis and Januszki's difference is an collection of the facet. So they think facet is a 1 point, but our case is an the facet is on some set.
Thanks for that question. The inverse image is 0 cross TL.
That's right. Yes, 0 cross TS. Yes. Yeah, yeah, yeah. Thank you very much. Yes, it's correct. Okay, okay. Let's continue. So anyway, so how to define the unimodular leveling? So now we have a local standard chart UM, and we restricted the point whose orbit is on a d-1 dimensional. Then we have the projection map from this. And so this MD-1 to the it's on a depth 1 point of the manifold UQ. Then this is a depth 1 point. So there is an map from this point to the this is an standard chart, positive O times RM, and there is unique coordinate. We call it the JS coordinate is 0. Then we assign the value of the this unimodular leveling as an plus or minus eta j. Actually, this eta j is coming from the actually this phi tilde is on a local standard chart. So there is an isomorphism which determines a weak equivalent condition. So we take it alpha 1 to alpha d, and this eta j is on a dual basis of this alpha 1 to alpha d. So this t hat is an up to sign. So this plus minus eta j is the same element in this t hat. So we give the unimodular leveling by this way, and that is okay. Okay, let's continue the third invariant. And a third invariant is we call it a Chern class of the principal T bundle over the this Q ring means an interior of the Q. Now Q is an manifold with faces. So topologically it's a manifold with boundary. So if we think it's an interior, then it's a preimage of the T action is on a free orbit. And a collection of this free orbit has the structure of the principal T bundle. This is a classical transformation group theory result. And this principal T bundle determines some element of the secondary cohomology of the Q with this Lie algebra coefficient, a lattice of the Lie algebra coefficient. So how to determine? So it is probably it's a well-known definitions. So now let's think about the short exact sequence of the sheaf. This TZ is a constant sheaf on a Q ring. Q ring is an interior of the Q. And this RD, this middle one, is a sheaf of germs of the smooth maps of Q ring into the RD. So now its Q ring is a manifold. So this is nothing but a collection of some smooth functions of the local chart. So now Q is a manifold. So we can take this a partition of unity. So we see that this is the fine sheaf. So the fine sheaf is one of the important consequences. Is a higher degree cohomology is vanished. So there is no cohomology more than 0. And this TD is an sheaf of germs of the smooth maps of Q ring into the TD. So by this short exact sequence, we can determine the long exact sequence. And moreover, there is no cohomology of the RD coefficient. So we can get this isomorphism between H1 over TD to H2 over this real algebra T. And moreover, okay. Moreover, this Q was an as a topologically, it's a manifold space, a manifold boundary. So it's homotopy equivalent to the interior. So and the Q and interior are homotopy equivalent. And now it's a constant sheaf. So this secondary cohomology is nothing but a singular cohomology. So it's isomorphic to the secondary cohomology of the Q over the lattice of the algebra. And now using this isomorphism, we see that this element of the secondary cohomology of the Q is correspond to some principal T bundle. Actually, this is a check one cocycle. So and this is on a check one cocycle. So this means that there exists a cocycle condition holds. So the element of this one is on the class of the principal T bundle. So this means that this principal T bundle is determined by this element C. So we call this C as a Chang class of the principal T bundle. So we determine these three invariants from the local standard T action. The first one is the quotient of T manifold, and the second one is a unimodular labeling, and the third one is on the Chang class. Okay, so and our main result is a roughly statement. Is these three invariants classifies locally standard T actions up to equivalent diffeomorphism. So this is still roughly statement. I will introduce a more precise statement later. And so this will be our main result. And to state our main result more precisely, I would like to introduce two important results. So probably the first important result is obtained by Takahiko Yoshida in 2011. He classified local standard T actions up to equivalent homeomorphism by using these three invariants. But in his case, he restricted this dimension of the M is twice of the dimension of 2M of dimension T. So in this case, there is no TL and RM part appears. So this is a classical local standard definition. And our next important example is by Bimera, Michael Bimera, in 2022. He classifies this local standard T actions up to equivalent diffeomorphism. But he gives an example under the assumption of there is a section from the orbit space to the M. So in this case, its principal orbit becomes a trivial bundle. So this the final Chang class is a trivial in this case. So he classifies equivalent diffeomorphism in these cases. And in this paper, he introduced a local standard action as the previous definitions. Okay, so this is our main result. Okay, let's continue the talk. So to state our main result more precisely, we introduced two categories. So the first category is denoted by M. That's a fractal M. This consists of its object is an locally standard T manifold, and morphism is an equivalent diffeomorphism. And the next category is denoted by Q. It's a fractal Q. Its object is an triple, which is Q is manifold corners, and lambda hat is unimodular labeling, and C is some element of the secondary cohomology. I would like to remark that if this is a manifold corners and which has an unimodular labeling, then it's automatically manifold spaces. So we do not assume this is a manifold spaces in this case. This is automatically manifold spaces if it has a unimodular leveling. And yes, morphism is an diffeomorphism in the sense of the manifold with corners, and which satisfies the following things. So this is an manifold with corners, and there is a set of the depth 1 point. So if restricted to the depth 1 point, then its unimodular leveling is preserved. So this is the first assumption of this diffeomorphism. And the second one is, of course, this preserves Chern classes. C2 is a Chern class of the Q2, and C1 is a Chern class of Q1. Okay. So I want to restrict this psi to the depth 1 point. So I will avoid the definition of the unimodular leveling as a collection of the facet. Okay. So this is the 2 categories. And okay, let's state our main result. Before state our main result, from the previous slide, we see that this locally standard T actions defines 3 invariant, say QM, lambda m hat, and CM. This is an object of the fractal Q. And then actually this gives a functor from the category M to the Q. We call it a classifying functor. So that is this object M goes to the this 3 invariant, and moreover, not only the object, but also the morphism is a descent to the morphism of the Q. And of course, the composition and identity satisfies. And then our main theorem can be stated as follows. This classifying functor is, the first condition is essentially surjective. So it means that for any object of the Q, there exists an locally standard T manifold M, such that its classifying functor is equivalent diffeomorphic, is diffeomorphic to the this triple invariant. And actually, this gives an existence of the locally standard manifold over the this triple invariant. Okay. So it's not enough to say the classification. To say the classification, we also need these conditions. Actually, this functor is full. And what is full means? Full means that for any it's an diffeomorphism between the invariant. CLM1 is an invariant of M1, 3 invariant of M1, and CLM2 is a 3 invariant of M2. And for any isomorphism between them, there exists an psi tilde. This is an equivalent diffeomorphism on the locally standard manifold, such that this descent by the classifying functor is equal to the psi. So this gives the uniqueness of such locally standard T manifold. Okay.
If I take M to be a projective smooth toric variety, and the invariants are Q lambda bar C, right? Which of those invariants is determined by the equivariant cohomology of the toric variety?
Equivalent cohomology. It's an we do not use an anyway. In a projective variety case, in a toric case, I think this C is trivial. So we need a Q and lambda hat equivalent cohomology to determine equivalent cohomology as an algebra. It's the algebra. It's okay. Okay. So this gives a classification. So we will prove this one in the next time. So first of all, I need to remark that this classifying functor is not faithful. So it means that the classifying functor full means that it's an morphisms are surjective, and faithful means morphisms are injective. If full and faithful and essentially surjective, then this gives two categories are equivalent. But it's not this classifying functor does not give an equivalence of the categories. So in fact, for the pi I is an orbit projection on the Q, I equal 1, 2. Then we have this kind of theorem. So let's take two morphisms, a diffeomorphism of the M1 to M2, says psi tilde and psi hat. And this descends the same psi, a diffeomorphism psi, which preserves a 3 invariant. This is equivalent to the following conditions. there exists a smooth map from Q1 to the torus, and this torus acts on M2. And this psi hat is twisted by this T, on psi tilde. So it means that we can take a different psi hat and psi tilde to, even if it goes to the same diffeomorphism psi. So it's not the first law. Okay, so this means that this classifying factor does not keep the equivalence of the categories. So we will prove our main theorem. This is also gives only gives an outline of the theorem because there are many technical parts. So I don't have much time to give any technical part. So I will just give some keywords of the technical part. So okay, let's prove the main theorem. So to prove the main theorem, we also use another category. This is called the P, fractal P. This is its object is a principal T bundle over Q. And we also assume this Q admits some unimodular leveling. And we denote it by this large pi. And its morphism is, of course, it's an bundle isomorphism. It means that there exists an equivalent diffeomorphism between P1 to P2, which satisfies the following two conditions. The first one is this F descends to the diffeomorphism to the Q1 to Q2, which commute with this projection. And moreover, there's a diffeomorphism here, FQ to the FQ Q1 to Q2, and we restrict the depth 1 point, say this part to this part, and this diffeomorphism preserves the unimodular level. Then this is an morphism of this category, and actually this is not so difficult. We say that this quotient is a quotient functor. Actually, this becomes a functor, and moreover we see that this functor is an essentially surjective and full. So this is the first result. And actually, this part is a technical part. So we can also define this functor from the P, category P to the category M. M was on the locally standard T manifold. So P is a principal bundle. So let's take the principal T bundle over Q, PQ lambda hat. Then we can get the cut space by the identifying of this principal bundle. So this is very similar to the construction of the Davis and Yanich grids to get the quasi-toric manifold by Tn times Pn. Okay, let's define it in the principal bundle case. So if we take the two elements from the P, say P and P prime, and P and P prime are equivalence if and only if these two conditions hold. The first condition says that P and P prime is on the same fiber. Okay, and the second condition says that not only is in the same fiber, but also fits in the same orbit of the Tx. I will define what is Tx. And this Tx is a subtorus, which is determined by the eta I1 to eta Ik. Actually, this eta I1 to eta Ik is determined by the unimodular leveling. So how to define it? So now we can take x from the, actually this is a local coordinate of the manifold with corners. And we say it's in Q, and there is an diffeomorphism to the open subset of the positive O3 times Rm. And now this x, we didn't assume this is depth 1. So there is some, we assume there is some k0 coordinates for x. And it's denoted by I1, I2, and Ik. And by using the unimodular leveling, this I1 corresponds to eta I1 for some basis of the TZ, and I2 corresponds to eta I2 by the unimodular leveling. Then we can get there are k elements in the primitive element of the Lie algebra, and this determines by taking its exponential, this determines a subtorus of the T. And if P prime and P is the same same orbit of the Tx, then we say this is an equivalent. So it means that if such kind of pointer exists, then we identify this point as a point. So it means that we crush this fiber by this Tx action. Okay? Now, actually, this is determined by lambda hat. So we get some topological space. Actually, we can get a topology by the quotient topology from a P. And the technical point is actually this cut actually this cut space gives a functor from the category P to the M. So this is the technical part. Because this P divided by tilde is, we don't know this is a smooth manifold or not. So we will prove this is a smooth manifold. This is a very technical part, typical part. Okay, let's give some outline of proof. The first one is actually this becomes a topological manifold. So we first defined it's a topological atlas in it. So by identifying the cut space, actually this cut space is defined from the U. U is an open set of the manifold with corners, and its inverse is an principal T bundle. So we can also do the cutting on this principal T bundle. Then we get some omega, which sits inside this standard chart. So this gives an topological atlas on the P over tilde. And the second step is a very technical part, but it's just on the keyword. To prove this atlas is smooth, actually this atlas gives a smooth structure on the P divided by tilde. To show it, we will use an argument of the Bredon. And in the Bredon's book, he classifies a so-called special G manifold. A special G manifold is a smooth G manifold whose orbit space is a manifold with boundary. To determine the smooth structure on it, he used some technique. It's not so difficult technique, but just using a Taylor's theorem. And we generalize his argument to prove that this atlas is exactly smooth. Okay, so then we get actually as diffeomorphism is goes to the equivalent diffeomorphism is not so difficult. So we get this is a functor. Okay, so this is the first result. And the next lemma is this cutting functor satisfies the following things. So the first one is this is an essentially surjective. Okay, so it means that for any locally standard T manifold, there exists a principal bundle, which is which cut space is equivalent diffeomorphic to the M. So we can prove these kind of things in the next step. And moreover, now we have three functors so far. So the first functor is an classifying functor from the M to the Q, locally standard T manifold determines the three invariant. And moreover, we introduced a cutting functor before. It's a principal T bundle, and its cut space is a locally T manifold. And so we have some composition functor from the P to the Q. So this is the first functor. And in the beginning, we also define the functor. It just takes a quotient of the principal T bundle, the Q, and we denote it as a pi. Actually, these two functor has some relations. It's called natural isomorphism. So these two functor is a natural isomorphism. So it means that this composition functor is natural isomorphic to the essentially surjective functor. So it means that this composition functor is essentially surjective and full and essentially surjective functor. So actually, this is also the some technical part, but another technical part. And to prove it, we also introduce a functor, which is an inverse from this cutting functor. It's the functor from the M to the P. So from the locally standard T manifold to the principal T bundle. So we call it a toric radial squared blow-up functor. So we denote it by BL. It's an abbreviation of the blow-up. And this functor satisfies this composition of the BL. BL is from M to P, and cut is from P to M. This is natural isomorphic to the identity functor of M. And the converse is an BL and cut is an naturally isomorphic to the identity functor of the P. So to prove it, this is also just a keyword. We introduced a simultaneous toric radial squared blow-up along the codimension 1 invariant submanifolds. So why this is a long name? Actually, this radial squared means that we distinguish this blow-up with an Yenix blow-up. Actually, I think the first person who classifying the G manifold up to equivalent diffeomorphism was Yenix. At that time, he also uses this kind of blow-up technique. But his blow-up, blowing up space is not compatible with an projection, orbit projection. So that is, it's an orbit projection is in a standard chart. It takes just an norm, just take norm, not norm squared. So it means that this projection is not smooth. So we want to see this is smooth. So we will use another kind of blow up. And also this simultaneous means that this is different from the blow up of Davis. Davis also defined this kind of blow up technique to classify the classifying G manifold. At that time, his blow up is an iterative blow up for the lower strata to the higher strata. Then he obtained some principal T bundle. And this is several steps. So we want to avoid this kind of steps. So we want to say just a one-time blow up. And then we have this kind of blow up. Then we obtain the some principal torus bundle P from the locally standard manifold M. So it means that for any locally standard manifold, there is a blow up M, which is sits inside this P. So it means that there is a torus bundle over QM. QM is an orbit space of the M. And also this lambda M hat is a unimodular leveling which is induced from the M. And this cut space is equivalent different to the M. So we can say this kind of things to introduce this kind of blow up. And now in the final step, as the final step, this is an more general, we can also say the more general categories, but we will restrict to our cases. There is a factor chasing lemma. So we assume that actually, let's say PMQ is a functor, and there is a functor, PMQ categories, and there is a functor from P to M and M to Q and P to Q, like before. Then let's assume that this composition functor CL and cut is essentially isomorphic to the pi. And moreover, we assume that this pi is an essentially surjective. Then this CL, this is the first functor, is an essentially surjective. And moreover, we assume that this pi is full, and this cut functor, this is the latter functor of this composition, is essentially surjective. Then we can say this CL is a full functor. So by using this functor chasing on the previous result, we can say the main result. So that is this classifying functor is essentially surjective and full. Okay, so this gives our main result. So this triple classifies locally standard T manifold up to equivalent diffeomorphism. So I have 1 minute. So in the final 1 minute, I will show you some example. So let's consider most easiest case. Let's take its orbit space as an interval, closed interval. Then it's an contractible. So its Chern class is always trivial. And now without loss of generality, its unimodular leveling is satisfies this first part. The first boundary is an eta 1, and the second boundary is an taking some element in spanned by eta 1 and eta 2. Now this eta 1 to eta t is a basis of Lie algebra. Then this M is the topology of M is dependent on this lambda hat 1. For example, in lambda hat 1 is equal to eta 1. Then this is a known result. M is isomorphic to S2 times TD minus 1. This TD minus 1 is obtained from the last T minus 1 coordinate of the basis. And if D equal 1, this is exactly the same with an toric manifold. And the next one is this one, lambda hat 1 is an eta 2. So as a generator. Then this M is an isomorphic equivalently diffeomorphic to S3 times TD minus 2. If this equal to equal 2 case, this is an exactly same with a moment angle manifold over the interval. And moreover, we can take this kind of element for lambda hat 1. Take minus W eta 1 plus K eta 2, because this element lambda this lambda hat must be the primitive element. This W and K must be a greatest common divisor is 1. So in this case, this M obtained M is a length space times TD minus 2. And actually, this length space is obtained by the free ZK actions by this way. Okay, so time is up. So these are references. So that's all. Thank you very much.